Hello and welcome. I'm Dr. Syed Mostafa Safavi, and you're listening to our podcast series on deep learning for intrusion detection. In this series, we explore how cutting-edge AI techniques are reshaping the way we detect and respond to cybersecurity threats. This podcast is produced with the valuable support of Alicia Tan, who has been instrumental in coordinating and preparing each episode. Now, let's get started and dive into today's topic. Welcome to the podcast. Let's dive into the intricate world of deep learning for intrusion detection and how deep learning meets high-performance computing, especially when you look at things like neural networks and even comparisons to something like Angry Birds.
That's a fascinating angle. Angry Birds, huh? So we're talking about complex mathematical calculations behind the scenes that require tremendous processing power.
Exactly. It's like imagine running a game where every little red bird, every slingshot trajectory requires, tons of calculations to get that smooth gameplay. And similarly, deep learning architectures, they need the same kind of precision in processing, from matrix multiplications to tensor operations.
Yeah, right. And it all starts with the neural network setup where you have hidden layers crunching numbers. You mentioned matrices. What's the connection there?
So think of each layer of a neural network keyed as a matrix, a set of weights and biases, where we do that calculation z charge sum, weight, input, plus bias, and then you apply the activation function. It's like turning raw input into a decision of whether a neuron fires or not.
Mm-hmm. And those operations, they're all about matrix multiplications, right? So the computing gets heavy, especially when you're working with large networks and billions of parameters.
Exactly. And you're not just looking at millions, but sometimes billions of parameters. It's like performing trillions of floating point multiplications and additions. No wonder GPUs come into the picture here. They're engineered to handle these matrix operations with ease.
Speaking of GPUs, I know that tensor cores and CUDA play a significant role. How do they enhance deep learning workflows exactly?
So GPUs, with their massive number of simple stream processors, are built for operations that rely heavily on matrix math. Tensor cores, for instance, are designed specifically to accelerate small matrix multiplications, like 4x4 blocks. Then they build up to higher dimensional operations, which is super efficient.
Right. It's like a well-oiled assembly line, where each small operation feeds into the larger computation. And all this is key for training neural networks, correct?
Yeah, totally. Training a neural network is compute intensive. We're talking about hundreds of thousands of input samples. And these deep neural networks require massive amounts of data to learn from. Every layer, from hidden ones to the output, is built with matrices that need constant multiplication.
Now, you mentioned something interesting earlier, the Angry Birds analogy, not only as a game, but also as a metaphor for computational complexity. Could you expand on that a bit?
Sure, it's like Angry Birds isn't an AI application per se, but it's a perfect example of how complex math, kind of the same math we use in deep learning, is behind every frame to make things smooth. The game's realism relies on intensive calculations that happen so fast. And similarly, deep learning not only requires heavy matrix math, but also a creative twist, imagination, to make the output something we find engaging.
Mm-hmm. I see. It's the same idea that even entertainment and advanced AI require both rigorous math and a creative spark to produce results that feel natural and effective.
Exactly. And when you step into the world of intrusion detection and even malware analysis, these principles persist. For example, instead of traditional signature-based detection, researchers are now leveraging deep learning to classify malware by transforming binaries into images and using image-based transfer learning.
Yeah, that's a cool term. And that brings us to the stamina framework, doesn't it? That's where they convert malware binaries directly into images, right?
Yes, STAMINA stands for Static Malware as Image Network Analysis. It essentially converts raw binary code into a two-dimensional grayscale image. From there, a deep neural network, trained using transfer learning, extracts deep features that help in discriminating between benign and malicious software.
Right. So, rather than dealing with complex binary signatures, the system treats malware classification as a visual classification task. That's such a creative reframe.
Absolutely. And it alleviates the heavy lifting usually required for feature engineering. The network learns the features autonomously, and because even malware samples from the same family share structural similarities, if you resize them, the visual patterns remain consistent.
Yeah, got it. However, don't you think there might be some loss of nuance when you resize these images? I mean, could it possibly affect classification?
That's a good point, but the research shows that resizing has minimal impact. The deep network is robust enough to extract features even from resized images, which is pretty reassuring considering the alternative would be an explosion of manual feature processing.
True. That makes sense. And the evaluation metrics coming out of such methods are impressive, correct?
Yes, indeed. The experiments reported an accuracy of about 99.07% with a false positive rate as low as 2.58%. These results really highlight that image-based transfer learning in malware detection is not only innovative, but also highly effective.
Wow, that's remarkable. 99% accuracy is no small feat in the world of malware detection.
Exactly. And it shows that deep learning combined with hardware acceleration can really push the boundaries of what's possible in cybersecurity.
And speaking of hardware, it's interesting how CPUs and GPUs differ fundamentally. CPUs have like a few powerful cores, whereas GPUs are designed with a whole battalion of simpler cores.
Right. It's like comparing a few heavyweight champions to an entire team of sprinters. CPUs are great for general tasks, but when you need parallel processing, like massive matrix multiplications, a GPU definitely wins.
And that efficiency is crucial for deep neural network training, especially when handling tensor operations. Now, tensors are just matrices, right? Or is there more nuance?
Well, it's like a matrix is a two-dimensional tensor, but tensors can extend to n dimensions. They are the fundamental data structures in deep learning. Google's TensorFlow, for instance, is built on the premise of manipulating these multidimensional arrays seamlessly.
Yeah, exactly. So everything from how images are processed to how models learn through backpropagation relies on these tensors and the math of matrix operations.
Absolutely, and that's why having powerful GPUs with specialized tensor cores is a game changer. They allow for rapid processing of these enormous calculations, making real-time deep learning applications possible.
Right. It's fascinating how every component, from hardware to the intricacies of neural network architecture, ties together in systems like malware detection.
For sure, and the use of transfer learning in this context really shows an intelligent reuse of existing knowledge. It's like taking a model pre-trained on millions of regular images and fine-tuning it to detect subtle differences in malware imagery.
Isn't it interesting how this method bypasses traditional methods like static and dynamic analysis, which have their own limitations like code obfuscation and long scanning times?
Yes, classic techniques struggle with modern evasion techniques, such as code encryption and obfuscation. Treating malware as an image sidesteps a lot of those problems because, well, structural patterns remain visible even after such manipulations.
That makes me think, while deep learning approaches are very promising, don't they also come with the challenge of explaining their decisions? How will we know why a particular binary was flagged as malicious?
That's a robust challenge indeed. Deep learning models are often black boxes, meaning understanding the reasoning behind a classification isn't always transparent. Yet, the focus here is on achieving high accuracy and low false positives. In practice, the trade-off between explainability and performance is something researchers are actively addressing.
Yep, that's an important consideration. And it's clear that as computational power continues to grow, leveraging these advanced techniques for cybersecurity will only become more prevalent.
Absolutely. And the integration of deep learning with high-performance hardware not only accelerates training and inference, but also opens up creative ways to tackle problems like intrusion detection and malware analysis. Plus, the continuous improvements in GPUs and tensor cores ensure that even future models can handle even larger data sets and more complex tasks.
Yeah, that's really something. So, looking forward, do you think we'll see even more convergence between advanced gaming simulations like Angry Birds and applications in AI and cybersecurity?
You might say it's less about direct convergence and more about borrowing concepts across fields. The same computational challenges like handling vast amounts of data and ensuring smooth performance show up in both gaming and deep learning. It's a testament to how interdisciplinary ideas continue to drive innovation.
Amazing. And for those who want to dig deeper, there's plenty of additional reading out there, from Intel's research on stamina to various articles on computer vision and threat detection.
Yes, indeed. The journey of combining deep neural networks, GPUs with tensor cores, and novel approaches like image-based malware detection is just getting more interesting. There's a wealth of exciting research that bridges multiple domains.
Definitely. It's been a really enlightening discussion, melding deep math, high-end hardware, and creative cybersecurity solutions.
Totally, and it's like showing that behind every smooth game or secure system, there's a fascinating world of computations, creativity, and constant innovation working in tandem.
Yeah, for sure. Well, thanks for that deep dive into the computational strategies powering intrusion detection and malware analysis. This conversation really highlights that even the most technical topics have a creative twist.
Absolutely, it's been a pleasure chatting about how math, hardware, and imagination come together in modern deep learning systems. Until next time, keep exploring the intersection of technology and creativity.